then, folks. Today we're going to be doing, we're actually going to be starting chapter 11, which is about probability. But according to the schedule, I should have been doing, let's see, 11.1 and 11.2 today. All right, 11.1 is empirical and theoretical probability, and 11.2 is about odds, which a lot of times people conflate those two things. They're very similar, but they're not exactly the same thing. I'm going to probably start 11.2, but leave the brunt of it for Monday of next week, and I'll do 11.2 and 11.3 at that point. Anyhow, for this section, what you'll need is another one of those blank sheets. This is some terminology that has to be covered. So if you would print something out like this, I'll make it available in Canvas naturally. And there will be another handout, well, two others actually. One that is a word problem, and another one that's a diagram that a table that I stole from your textbook. Anyhow, let's get started. Let's see. Put that there. All right, and we'll do this. Okay. I'm gonna move this temporarily and pull out, let's see, the sheet, if I can get it to fit back here. And we'll get our terms out of the way. Okay. And I'll erase whatever I need to. All right. Doing 11.1, of course, but let's make sure that the terms are all in one place. Losing ground here. Okay. I think I have not enough of a ledge here, so I'll take this out. Put that down. Okay. And continue. My cardboard is apparently not level. Right. Anyhow, let's get that over there. Centered. Good. Alright. Alright. Let's see. Let's start with this. All right. In the concept of probability, you will hear the phrase experiment. Perhaps I should capitalize to make it a little bit easier to see. Okay. An experiment, it has no generalized symbol, but it's officially a controlled operation that yields a set of results. And I'm putting sets in the traditional fancy braces because technically you would collect things, the results. This is struggling to fit. The results. I'm sorry if that is a little bit too faint. And is it legible? I'm trying not to write in script too much because I think it's bunchy. Alright, there's a bug here, sorry. Away fly. Alright, anyhow, we don't think of a game as being synonymous with an experiment, but mathematically, in the context of mathematics, they are exactly the same thing. So when you think of an experiment for probability, really think of a game. All right. Then there are outcomes. There's a term that gets used. Basically, the outcomes are the results, right, of an experiment. Any result. Right. Any result of a game is referred to as an outcome. Okay. When you get into the formula, there's two, you'll see, no, three. Formulas for probability, they use the letter E a lot. right? And E is referring to an event, an event. Okay. An event is officially any subset of possible outcomes. And what does that mean? Remember subsets from, I think it was chapter 1 or 2, earlier in the semester. A subset could be the empty set, right? A subset can be all of the elements. A subset could be some derivative of them in groups of 2, in groups of 3, however many elements is really what determines it, okay? So however you bunch together the results, all right, you would refer to that as an event. Could be 2 things simultaneously, and you'll see a couple of examples to that effect. Then there is actual probability, all right? Probability is abbreviated like this, as a P, capital P, and a parentheses. The element letter is usually fitted into here. But let's just start with a generalization. You would read this as the probability of, and then whatever is inside the parentheses, whatever the specified event is. Probability. Okay. It's basically a number. I'll put this specific in that dark enough. Can you see it? All right. A number used to describe the likelihood of an event. I'm kind of squeaking this in here, but a number used to describe the likelihood of an event is a probability. That's basically translating, its job is to translate something that is an actual game, an experiment, something that happened in the real world, into something that is purely symbolic, all right, and mathematical. All right? Often it is just a fraction. All right? All right. Now, as for the specified types that I alluded to before, all right, empirical probability and theoretical probability. Let me just give you the definition of empirical probability, which would be really indistinguishable from theoretical in terms of the symbol, but the formulas are a little bit tweaked slightly. All right. When you think empirical probability, think frequency. They use this term, relative frequency of an event actually observed. That's the key there. This is something that is actually observed. Right? If we're talking in the language of science, and we use the when we're talking games, we call them experiments in that respect. I don't think of an experiment as being a game, but it can be fun, right? An experiment is done in trials, right? At least if it's done well, multiple times, all right? And the more the merrier, all right? Anyhow, when you run an experiment, often what happens is the unexpected happens, all right? Anyhow, how often something occurs, all right, in real life, what is actually observed is more accurately referred to as empirical probability, all right, as a result of several trials, as a result of several tests, all right, not just once. All right. Then there's this, theoretical probability. I'll get to some diagrams. Again, this is indistinguishable in terms of its abbreviation from empirical probability. this is mathematically calculated. Without an experiment. So without doing something in real life. Mathematically calculated without an experiment. All right. That's basically all that you would need to know in order to get through section 11.1. All right, so I'm going to put my definitions away for a moment, and I'm going to try to organize the information into a diagram. Some of it the same information, but more specific. All right, let me get rid of this. Put this aside. Go back to my larger ledger here. Okay, is that in frame? Good. Blue is misbehaving today. Usually the green. But I came prepared. I have an alcohol wipe. Let's discuss experiments. There are 3 basic probability experiments, which again is just a, it's a fancier way of saying games. You're inclined to see. There's the good old coin flip. And the die roll, and the card drawer, and just to illustrate that point, I try to dig up some toys I had. A coin flip is obvious, right? It's a little hard to demonstrate. I took some change, right? Stood on the corner and went, "Hey, help!" And you should, not me, but whoever needs it. A lot of times you use a quarter for this purpose. Let's see if I can flip like Two-Face from Batman, right? Without losing it. Not bad, getting there. Anyhow, it's a little bit hard to see, unfortunately, if the coin is not that big. These are dollar coins, so I like the Sacagawea, quite frankly. I wish they would bring that back, because that to me was the nicest coin that we have, right? Rather than those doofy presidents. A lot of them were terrible people. She was actually a nice person, right? But here is another one. This is I wish it's not my favorite silver dollar, but I used to collect coins as a kid. This is Eisenhower, right? President Eisenhower. It's a larger silver dollar. It's actually silver, right? This is a little bit easier for the purpose of demonstration, coin flipping. Right. A little bit heavier though, right? And it makes that distinct noise, right? Anyhow, when you have a coin flip, all right, there's the head naturally, and there's the tails. All right. This was, although dirty, this was 1971. This coin came out, so there's the eagle has landed. This is to memorialize the moon landing. It's a little bit hard to see. There you go. Get the light like that. The American eagle on the surface of the moon. Anyhow, in terms of outcomes for the coin flip, how many are there? Right? There are distinctly 2 outcomes that are possible, right? Which means that if you were going to categorize them into a set, right, it's only 2 things. It's heads or it's tails. All right. Can only be 2 possible outcomes. There was an episode of The Twilight Zone years ago with one of the actors from Bewitched, that he flipped a coin to pay for a newspaper, and it landed rather flat on one side or the other. It landed straight up, you know, like that. And then for the rest of the day, he could hear people's thoughts, which is inexplicable, right? But it was a Twilight Zone. So it's kind of a cool episode. I forget the name of it offhand. But anyhow, that almost never happens, right? So we don't even consider that really of a coin landing on its edge when tossed, right? We think of it as being basically two choices, two options. Heads, that one, and tails. Right? And therefore, that's what the set looks like. Okay, as for a die roll, I dug up my Monopoly, because I have no dice laying around, right? And you know what, this is stupid, but it's made by Parker Brothers. Nowadays, I think it's Hasbro. It's funny how that changes over time. There is no Parker Brothers. In here somewhere is Uncle Pennybags, some Monopoly money, which I'm going to try to spend later. It's all disorganized. No time for this. Anyway, here are actual dice, right? That being the plural in English. One is a die, all right? And since there are 6 sides, the most that you would see is 6 dots on a side, sort of like a domino, right? In Monopoly, they have 2 dice because it will get you around the board a little bit more efficiently than just 1. Anyhow, what does anyone do? You roll them, right? In this case, it rolled a 2. I'm losing the edge of my thing. In this case, it rolled a 3. To illustrate the point of a die having obvious sides, right? I just dug up my Rubiks Cube as well, right? Only for the reason, this is not a die per se, and it's carved up into 9 blocks each side, but the one thing that's nice about a Rubik's Cube, at least, is that it is a cube, and it has painted sides, so you can see that there is one distinct from another. Anyhow, that'd be really cool now. I wish I could get it to spin indefinitely. That would be really great. Anyhow, the way that they designate a side, or distinguish a side one from the other in terms of a Rubik's Cube, is to paint it, rather than to put dots on it. But I could say, right, if you saw 1 dot on one face of the cube, and that is side number 1. And if you saw 2 dots on a different side of the cube, then you would say, okay, that's side number 2. All right, and so forth. Anyhow, in terms of number of outcomes, there are 6 possible outcomes for a single die, right? Which means that if you were going to, again, collect a set of possibilities of outcomes, all right, it would just be the numbers to represent the sides. So 1, 2, 3, 4, 5, 6, and that's it. And my red is off the die. Okay, that's the dud for today. There we go, that's a little bit better. Okay. 4, 4. All right, there you go. So there's that. When it comes to card draws, that's a bit more complicated. All right, the reason being that there are different types of decks of cards. All right, these two are both the same type. All right, they're not just that the designs are different on the back. Like for example, I want to say these are probably made by the same company. The back design of the cards is really irrelevant. Right. These are a little bit fancier. These have white snakes and stuff like that on them. Yeah. But these are poker decks. Right? Poker as opposed to like a pinochle deck. I've never played pinochle, all right? But it requires different denominations of the various card types. Let me put these dice in here not to lose them. And Monopoly can vamos. Lose my Monopoly. Anyhow, it occurred to me, and if you go into teaching, I have to tell you, don't ever assume, all right, because I have made this mistake, that a kid, all right, especially a little kid, has actually ever played cards, right? I took it for granted because I lived with my grandparents and I've been playing cards since I was like, you know, at least 5 or younger. Even if it was just like, you know, organizing them. I took it for granted some years ago when I started teaching in college that, pretty much everybody has seen a card, you know, their deck of cards because it's ubiquitous, all right? And it's not true. There are people who, you know, maybe they're just not that lucky, you know, they're not privileged, right? They haven't played that game. No adult in their life ever said, hey, listen, you want to play cards, right? Anyhow, which makes teaching this subject, right, probability via card draw, that much more difficult. You have to introduce, all right, the deck to them, even if that sounds silly. Yes, there are instructions in the deck, and that's irrelevant. This advertisement is also not necessary, and the jokers are going to come out, which there are 2. Anyhow, if you've never seen a deck of cards, all right, they have a nice design on the front, usually, and there are these possible types of cards, right? Without showing you every single one, there are some that are drawings, right? They basically represent the numbers 1 through 13, all right? But some of them are labeled that way and some are not. So let me just, not to get this all over the place, put this away and make sure that you're clear about this, all right? In terms of outcomes, there are technically 52 unique outcomes in a poker deck, all right? And that's usually when you go to the grocery store, the supermarket, that's the thing that is on the shelf, right? In the school supplies aisle, you know? They have fewer pinochle decks. I'm not sure how many cards are in a pinochle deck. I can only tell you that it is different, right? There's different amounts of the cards. Anyhow, for all intents and purposes, there's 52 unique outcomes, all right? There are some things that are similar about the cards you will notice as you go through them, all right? But to summarize, all right, in terms of their set, and this would be quite involved, right? They have an ace of, you know, say something like spades, all the way through a king of spades. And I'm just drawing as close to the shape that is a spade as possible. What that really means is ace as in the number 1, all right? And the K, which is the king, is in 13. All right. In between, there's 2, 3, 4, all right, 5, and then you get to 10, and then they have picture cards, the king being the last of them. Anyhow, the jack would technically be 11, and the queen would technically be 12, all right, and the king would technically be 13. They're just not written as a number in that case. That's just of one suit, all right, which is the, you know, the spade suit. Just let me elucidate this a little bit more. 6 all the way up to 10. All right. Numbers 2 to 10 are actually labeled as a digit. All right. Then there's, as I mentioned, a jack, a queen, and a king. And that is 11, 12, and 13 respectively. All right. Then there are the other suits, because there's 4 suits. So you would see an ace of hearts. And they'd have all the same things, a jack, a queen, a king, all the way up to that. And then another black suit, which is clubs, which kind of looks like a clover, something like that. And again, all the way through the numbers up to jack, queen, king. And then lastly, diamonds. All the way up to jack, queen, king. All right. So that's why if you consider them you know, according to simultaneously a color, a number, all right, and a suit. There's 52 unique possibilities when you're pulling cards randomly out of the deck, all right? Again, as a person if you're going into the profession of teaching, all right, sadly, do not assume that a kid has ever played cards, all right? I have made that mistake. All right. There's a technical term for this. It's really not super important, but we call things like this, you see here, heads or tails or what have you, a set. And I like that because it's simplistic and it gets the point across. The contents form a set. In statistics, they use a different word, right? And sometimes probability certainly comes up in the course of statistics. They will alternatively refer to this as a sample space. Just realize that a set, a sample space, an experiment in general, these are synonymous. Okay. All right. Those are the kind of questions that you're inclined to see. Questions about coin flipping, die rolling, and maybe technically card drawing. All right. Let me erase this and give you the formulas now. Wet this, especially when it comes to that type. Okay. I hate doing this, but bear with me. Blue's right nice, but I'm giving me trouble today. Moving on. There are, unique to this section, two main formulas to describe the two types of probability. All right. Let's go into details about that. I might could get rid of this at this point. All right, as mentioned earlier, there's theoretical probability. And there's experimental. Okay. And just want to make sure these are separated, so I'm giving myself a little line of demarcation here. All right. The formula as it would technically look for theoretical probability would be this. Right? It would be a P with an E on the inside. Probability in E is just a generalization for an event, right? Whatever the experiment it is. Certain event. And the rest of it would look like this. And I'll explain this in a moment. All right. To kind of give you a basis for comparison, the probability, the experimental probability would use the same abbreviations, P parentheses E, the probability of E, which is how you would read that. Whatever is in the parentheses. But the formula is simplified to this. And they are going to essentially accomplish the same thing. As you can see, in its most basic form, you know, what type of number does this line imply? A fraction, all right? What is the probability? But it's a number used to describe the likelihood of something happening, an event occurring, all right? There is still, nonetheless, this line separating a top number from a bottom number. So it is a glorified fraction, is what it is. All right? Anyhow, if a person is told to use theoretical probability, or they decide based upon the conditions of whatever they're doing, the question, all right, that this is more appropriate than that, then this is how you would read this, right? N as in number, and E as in the specific type of event. Okay. That is a number. So it's the number of the specific events that are possible. All right. The number of outcomes favorable to the event. Okay. Is what this is all designating or signifying, right? The number of outcomes favorable to the specific event under scrutiny. Okay. This, which is written on the bottom here, I'm going to put it in black, is the total number of possible outcomes. Okay. Basically, theoretical probability is the situation when you are not doing an experiment. You're doing an experiment in your mind, maybe, what you might call a thought experiment. But don't use the word experiment because people will conflate the two. And they shouldn't. They should distinguish them. Anyhow, all right, when all outcomes are equally likely, they're seemingly equally likely, we would go with the theoretical situation, right? The possibility of drawing, of rolling a 6, right, is just as good as, say, rolling a 4 or a 5 or a 3 or a 2 or a 1, you know, on a die, right? We could do that in our head, all right, without actually performing the experiment. If we physically took a die and rolled it and observed what the result is, then we're doing an experiment, all right? All right, and in which case, what is this F? It's the frequency. That's why the F, right? Or you might say the number of times the event is actually observed. The N, on the other hand, is the number of trials. You might say the number of games, rolls, draws, flips, experiments, to generalize trials of the experiment, right? Tests, if you will. Anyhow, because of the nature of experimental probability being dependent upon what is actually observed, all right? The result of experimental probability, at least in the short term, is likely to be different from what theoretical probability predicts, and that's not anybody's fault. It's just a natural occurrence. There's a definition in your textbook which is called the law of large numbers, which means that these two things will be different for individual results, all right? If you have only a few trials, you're really not going to see the same number as the theoretical probability. But if you do enough experiments, eventually, if you do really, really large amounts of the experiment, eventually they will coincide. They will be the same number, or at least very close to it. All right. When there isn't a possibility of determining something theoretically, right? You may have to do an experimental probability. An instance of that would be something like life insurance. Life insurance companies, sadly, all right, will use experimental probability to determine the chance of a person living to age 65. All right. Based upon their job, their vocation, right? A person who, for example, say he works in a coal mine, all right, they're exposed to hazardous, waste basically all of the time, if nothing else, the debris from the mining process, black lung, right? So, sadly, not to sound like a man of doom and gloom, but a person who is working in industry, all right, their likelihood of living to the age of 65 is probably slimmer, all right, than say a person who works in an office, all right. Anyhow, there are the conditions that are potential factors for their longevity as well, what their diet is like, all right. Anyhow, life insurance will use experimental probability to predict the chance of a person living to the age of 65 based upon their job that they do, all right? So they will take data, all right, and basically look for the mortality rate of people according to their vocation, all right? It's an experiment, all right? They can't really do it theoretically otherwise, right? So they have to look at actual results, right? Which would be better classified as being experimental. Okay. Now, this is, I said, section 11.2 is odds, and they sound very similar. So what I'm going to do is kind of broach the subject now. I'll show you the difference between them, all right? But really only do probability questions today, all right? And we'll do odds on Monday. Do the odds. Good enough. Okay. All right. Here are some facts. If I could turn this, my camera's drooping, so I'm gonna adjust my little pocket protector that's holding this up. There we go. It's a little bit better, right? Okay. Here are some facts. All right. Probability versus what you might have heard or you will hear this term in English, odds. They are similar but not exactly the same thing. Okay, what we're interested in, and this is section 11.1, and what is coming, this is section 11.2. probability is presented mostly in the style of a fraction. So it's mostly written as a fraction. That's the first thing. So there'll be an obvious top and an obvious bottom, something that looks like that. Right? Both of the formulas that we have look like that. There's a top number, there's a bottom number. Odds, on the other hand, they can be written as a fraction, but to distinguish them perhaps, they are mostly written using a colon. Which is more or less calling it a ratio rather than a fraction. A fraction is a specific type of ratio. The conditions to be a true form fraction are a little bit more strict than what they are to be a ratio. A ratio can have decimals in the top number and decimals in the bottom number, never mind what they work out to be if you actually divide them. Anyhow, perhaps again to distinguish one from the other, rather than use that line, all right, what you will see when we're speaking of odds is the two numbers that are involved on opposite sides of the colon. So more or less as a ratio. All right, rather than say a fraction. Even though they are, one is a specific example of the other. Okay, now, another thing. Probability, if it's a fraction, can be translated into a percentage. All right. Now, if you're a little bit iffy about that, do you remember a while back we went through this? There's a diagram I had given you, how to convert from either a fraction or a decimal to a percent. In both cases, you're really just doing what? You're multiplying by 100 if you're starting with decimals and going to percentages. You're multiplying by 100 if you're starting from a fraction and going to a percentage. And then you just remember to leave that symbol, which really looks like 100. Anyhow. These, on the other hand, odds, right, should never be written in the style of a percent. Never do that. All right? The reason being is that the odds, based upon the way that they're presented to you, and it might be for nefarious reasons as well, because this is for gambling, they might be presenting you something that exceeds 1, all right? And the fact of the matter is a percentage really should not exceed the amount of 1 or 100, which is the equivalent as a percentage, all right? So it's perhaps purposely misleading. What does this entail again? To translate from what it is, a fraction, to a percent, you multiply by 100. So you can make it look like 100 over 1 if necessary. Or you do the actual division and you get a decimal. And the effect of multiplying by 100 is simply moving a decimal point twice towards the right. We'll see in a couple of examples. Okay. Now, why is it okay to translate probability into a percentage? Because there's a maximum that the probability can be, and there is a minimum. The maximum of a probability, and I'm just going to use this as a generalization, P parentheses E, would be exactly equal to 1, which means that it's 100% in the style of a percent. That means that something is absolutely certain to occur. The minimum, again, just generalizing here, P, E, would be 0, which means, in the style of a percent, 0%. All right, which means never going to happen. Just mathematically impossible. Okay. On the flip side here, you might say, why not? Why not? Why can't you present an odds in the style of a percentage, or why shouldn't you anyway? It's because, I alluded to, it can exceed 1. The amount of 1, which in the style of a percent would be something greater than 100%, which is not really possible in real life. All right. At least it shouldn't be. Anyhow, odds are, maybe I shouldn't jump to conclusions, presented to you in either terms of good odds or bad odds for the sake of deciding how much a person gets paid out as a result of the game. The context is different. For right now, I'll drop it and I'll leave it at that. The context of probability is what is possible, right? The fraction is describing what is possible, all right? Odds, the context is in terms of in favor of something or not in favor of it, or against what they would say. So good or bad odds. Anyhow, it is slightly misleading the way that this is actually written. Because if you translated it to a fraction and then converted it to a percentage, it would be like, oh, the likelihood is somehow better than what it is in reality. Right? Probability is closer to reality. This is about gambling for the sake of deciding how much money you make as a result. Just to kind of squeak this in here, for probability. The probability could either be 0, this is summarizing these 2 points, exactly equal or something greater than 0, but on the flip side, exactly equal to 1 or something less, right? This symbolizes this basically, right? And the sum of all probabilities, which is sometimes symbolized by a sigma, is equal to 1. That is the maximum again. All right, let's do some examples. I'm going to start with theoretical because that you can do without experiment. Space to write? No, probably not. Alright, I'm going to erase this reluctantly, but I must. Let's do some examples of theoretical probability, which for whatever reason I have subconsciously decided is blue. several of these. Right. Suppose that you were asked, theoretically, right, to calculate the probability of rolling a 2 on a 6-sided die. Start with the formula. Here's our general formula. And we will tweak this. You don't have to really go crazy, but I think it is a good habit of trying to assimilate whatever the problem is uniquely to the formula. So, if we are trying to calculate the probability, the theoretical probability, without actually rolling a die, you know, I would sort of write it in shorthand like this. Put 2 in quotation marks, right? Because 2 is referring to a specific side. And do the same thing here. Leave this as an S, right? Unless you want to specify this is the number of outcomes in the sample space. And this is the number of events favorable the number of outcomes favorable in this unique situation. Okay. How many sides of a die? I'm taking a look at one die again. How many sides are actually labeled 2? Just 1, right? So that's unfortunate that, you know, we're using the digit 2, but there's only one side that is actually labeled that in dots. So the number here, the number of outcomes favorable to rolling a 2, all right, is 1. What are the total number of possible outcomes, right? How many sides are there on the die? There's 6, right? Because it's a 6-sided die at least. As opposed to, what do they call it? Like a Dungeons and Dragons die, which is, I want to say, like a dodecahedron, so like a 12-sided die. That doesn't come up too often. Anyhow, that is the fraction then, right? It's 1/6, right? Which again, if you want to put it in terms of a percentage, translate this to something perhaps is a little bit more presentable, a little bit more meaningful to a human, all right? Remember, you could convert the fraction to a decimal and then multiply by 100, and that will express the same quantity in the style of a percentage. This is the train of thought. How does one convert from a fraction to a decimal? Basically, it's the top divided by the bottom. So the numerator divided by the denominator. And you would take a calculator, 1 divided by 6, and you would see this. Right. You would end up with basically 0.16666 forever and ever and ever. All right? If you multiplied by 100, the effect of multiplying by 100 is that it's just going to scoot the decimal place over twice towards the right. So that means that this is really 6.6 repeating percent. Right? You could round it perhaps if you want. You could say there is a 17% chance die and getting a 2 specifically. As a matter of fact, and that's not very good odds, don't use the word. It's not very good probability, right? Because I actually got a 5. There it is now. All right, all events, all are equally likely though. Okay. Yeah, complete the thought. Sorry, I'm throwing things at you. All right, let's do this. I'm not going to raise too much. Assuming that we're using the same die, just tweak the question, augment up the ante ever so slightly. This is getting dark. I'll move the, put the lights on. All right, what is the probability of, say, rolling a number less than 5? Something smaller than 5. Now, it might help to sort of draw the set, right? We're talking about the same 6-sided die. The set is 1, 2, 3, 4, 5, 6. And the formula is still this, to generalize. Right. The number of events, the number of outcomes that are favorable to the event, right? And the number of elements in the set, or you could call it the sample space. Right? If I were going to sort of take this generalized formula and rewrite it so that it is specific to this particular problem, then I might write it like this. The probability of rolling a number less than 5. I would squeak that little abbreviation that I had conceived of inside the parentheses here, right? It isn't super important, but it is an interesting mental exercise. Kind of fun. How would you, like, going through the process of how would I abbreviate something? Okay, and that is the same thing that would be here. The number of outcomes favorable to the event of a number less than 5. Now let's see. Let's do the easier thing first. All right. The number of the number of all possible outcomes in the set, in the sample space, are these. 1, 2, 3, 4, 5, 6. That is almost never going to change. All right. So our denominator is still 6. All right. The number of numbers that are, or sides or faces, whatever you want to call it, that are less than 5, though, are how many specifically? All right. That's less than 5. That's less than 5. That's less than 5, and that's less than 5, and that's pretty much it. So how many are there? 1, 2, 3, 4. The fraction changes to 4 over 6, which if you wanted to, you can simplify to 2/3 using GCF of 2 to divide the top and the bottom, all right? And then go through the process again. For the sake of presenting it to another person, look, here's what the probability would be in the style of a percent, because humans tend to prefer percents. That's why in the news, you often hear percents thrown around. Why? Because it's relating something to 100, which is kind of silly to say this, but a more warm fuzzy number, all right? So what is 2/3 in the style of a decimal? If you divided 2 by 3, you would get 0.6666 forever and ever and ever, all right? which again, if you multiply by 100, would just move this decimal place over twice, right? And you would have this 66.6 repeating percent, which is about equal to 67 if you wanted to round it to a whole percent, all right? Which is pretty good, all right? If I were to roll my die right now, all right, based upon that number of 67%, I'm probably going to get something less than 5, all right? It's not impossible to get something else, but if I did this a couple of times, it's probably going to be something that's a 4, a 3, a 2, or a 1. We'll see, all right? Guess what number it was? 5 exactly, all right? Individual events? No, here's a 4, all right? All right, this is experimental probability now. 6, all right? So far, not looking so good, all right? Here's a 3, 2 for 2 at this point. Yeah, 6 again. 3 again, 50-50, still, and I want to hit the 4. All right, 4. All right, anyhow, just bear in mind, the experiment and the theoretical probability, at least for a low amount of tests, a low amount of experiments, are probably not going to be the same result. They're not going to be the same fraction, they won't be the same percentage. But if you did the experiment 100 times, you know, they should match or get as close together as possible. All right, there's a diagram I'm going to show you later. One more of these. Well, 2 more. What is the probability of rolling an odd number? Again, I would start with actually drawing out the set, the sample space, the elements 1, 2, 3, 4, 5, 6, just for the sake of comparison, all right? Comparing. Okay, here's our generalization again. N-E with an N-S. Okay. To make this a little bit more specific to our problem, the probability of rolling an odd, this is a fairly good, concise way of explaining this verbally versus symbolically. Okay, and in that event, okay, the number of outcomes favorable to the event of rolling odd, and the sample space here. So let's see. The number of elements in the set, the sample space, 1, 2, 3, 4, 5, 6, still 6. All right. The number of things that are odd. 1 is an odd number, 3 is an odd number, 5 is an odd number. All right. How many are there? 3. So 3 out of 6. All right. Which is really a half. Which is really wider than the style of a percentage. 50%. Still, you know, equally likely, odd or even. But certainly better than 17%, you know. I wouldn't bet money on 17%. I might bet money on 50. I would definitely bet money on 67. Okay. Now this is kind of a trick question. This last one. What is the probability of rolling a 7? Sometimes you get goofy questions like that. I guess they're testing to see if you're paying attention or not. All right. Well, you might write it like this. And if you do, it might help elucidate, clarify. The probability of rolling a 7 would be equal to the number of outcomes favorable to rolling a 7, that specific situation, event. All right. This is still 6, of course, because we're still talking about a 6-sided die. But now here's the question. On a 6-sided die, not a dragon, what's it called? Dragon Ball. On a Dungeons and Dragons die, right? There are, I think, 12 sides. I don't know for a fact. Are there any sides here on a single die that produces or is designated 7? None. So it's kind of a trick question. So you would say, well, the number of events favorable to rolling a 7? 0, right? And as long as 0 is the numerator here, all right, what is the answer? It's like 0 divided by 6, which in terms of a percentage is 0%, which means never going to happen. Never. Right? You'd have to have a 7th side. And there just isn't one by design. Okay, let me give you 2 more formulae, and then we're going to do something kind of fun. A word problem. Still theoretical. Because again, the real difference between theoretical and experimental is that experimental is actually doing a test, actually playing the game. It's real life versus just in your head. Okay. There are 2 more formulas here. I'm using Latin here, as opposed to S-A-E, which I want to say is pronounced I. At least that's what I remember being taught, right? Correctly, perhaps, or incorrectly, we'll see. Here is a general formula. Formulae. Google would disagree with me, but I'm going to go with what my professors taught me. At least with my Latin professors, I had a lot of respect for them. This is how, as your textbook writes this formula. And I'm stylizing this 1 here just to make it obvious that it's a 1. Okay. Here's the first one. All right. The probability, I'll just sort of quasi-write this verbally. This thing here, it's in blue. The probability A will occur is what this is symbolizing. Plus the probability A will not occur is equal to 1 whole, because that is, although it's very general the way it's expressed, taking into consideration everything that is possible. Can A occur in some experiment? Perhaps. All right. Can A not occur? Yeah, perhaps. One chance being perhaps better than the other depends on the experiment. But that's the maximum for probability, 100%. Taking into consideration everything, right? And this is a generalization of everything, what is and what will not be, right? All right. In other textbooks, they use a different symbol, right? And so if it just comes up, what they might do instead of actually writing the word not, is they will do this. they will put a little tick mark next to the letter A prime, right? It means that. All right, so if you see something like this, A, the probability of A prime, it means the probability A will not occur. It means probability of not A. Okay. If you take this formula and you rearrange the parts algebraically, you get something that is possibly more practical, which is this. All I've done in this case is basically move the probability that A will occur over to the opposite side of the equation of the formula, right? In which case it would be subtracted on that side, assuming it's positive on this side, and it pretty much has to be positive. All right? You will never have a negative probability. No negative fractions. It's either 0 or something bigger than that. Anyhow, there's a name for this formula, and it's going to be useful in the word problem that you see in a few minutes. It's called the probability of the complement, or of a complement. If you've ever seen geometry, you've probably heard this term before, complement. Two angles are said to be complementary when they work together, right? In which case, in terms of geometry, they add up to 90, or two complementary angles. Supplementary is another one, they add up to 180. The probability of a complement is two things working in tandem that equal 1. All right. Anyhow, if you were asked this question, right, what's the probability of something not happening, right, you could subtract the probability of when it will happen from 1, because 1 again is the maximum, and you will get the balance, basically. It's doing subtraction rather than a lot of adding. All right, now, to kind of get your feet wet on this, there is a handout of a word problem that looks like this. I labeled it like so. A 2-pound bag of Hershey's miniatures candy contains these candies. I had to, unfortunately, write this was my printer ran out of black ink. 33 milk chocolates, 27 crackles, which is like a crunch bar, right? 26 Mr. Good bars, which is milk chocolate with peanuts, all right? And 19 special dogs, which is the one that I actually like. That's the ones that go first if you have that candy, right? At least in my house, yeah. Right? There'll be a bag of all crackles or whatever, or all Mr. Good bars and nothing else, right? If you were to find the theoretical probability, right, we'll find it for these conditions. What is the probability, theoretically, of drawing a Mr. Good bar? What is the probability of drawing a crackle or perhaps a special dog? And what's the probability of not drawing a milk chocolate? In which case we'll use that formula. This is going to get a serious cleaning later. All right. If you want, you don't have to do this, but to answer these word problems, all right, here's what the set would look like, very abbreviated. 33 milk chocolate, 27 crackles, which are not bad. I really don't mean to diss them, but they're not my favorite. I'd rather have a crunch. 26 Mr. Good bars. Mr. makes you wonder whatever happened to Miss Good bar. All right, maybe that's what crackle really is. Who knows? Let's see. 19 special dark, which is the good one. All right. Most of these candies suck. I'm sorry, I shouldn't say that. They're okay. You know what? Chocolate is chocolate. You know, like we can not eat it. You know, if it's laying around, you'll be like, oh, especially since, you know, Easter just passed, right? So you have a bunch of like Cadbury eggs in your life. And like you open up the carton of regular eggs, you're like, ah, one of them is chocolate. I get all happy when I see candy. Anyhow, to answer these questions, let's do this. A was, what's the probability of drawing a Mr. Goodbar? So I should stick with my own system here. I think I'd rather just eat peanuts in that case. Let's figure it out. Okay. The probability of drawing a Mr. Goodbar randomly, the theoretical probability, right? Mr. G, not the weatherman. Well, it would be, let's see, 26, right, for the top of this fraction, right? But then we need to figure out what's the number in the set entirely of individual pieces, right, generalized. In which case, you're going to have to add all of these together, right? 33, 27, 26, and 19. That sum. Okay. And in that event, it would be 26 over 105. Okay. Which is not really a warm, fuzzy kind of an answer, even though it's correct. So what would you do? You take that and convert it to, if not a simplified fraction, something that is a percentage, right? Because it's more meaningful to go on, right? Better than 50 is a good chance. So, what would happen if you took your calculator and divided 26 by 105? Is that you would get this decimal, right? 0.24. 7619, something like that, which if you multiply it by 100, the effect will be to just move this over. Which means what? It means that it's 24.76, whatever it is, percent. If you wanted to round it, I mean, if they don't specify, maybe round it to a whole number. You'd say it's about a 25% chance. Just randomly sticking your hand into a bag of Hershey's miniatures and going, voila, Mr. Goodbar. Okay? 25% chance is not that great. Okay. But it is possible because it's not zero. Here's B. All right, this one is more interesting. Because it's two things in tandem, right? The theoretical probability of drawing one of two things, a crackle or a special dark. So you might signify that like so. P parentheses crackle or a special dark. And that is still n, it's theoretical probability n parentheses e over n parentheses s. Okay. The number that we had gotten from adding all of the individual pieces, all right, is still 105. That's not going to change. But this number that is taking these two things into consideration, that is going to change. All right? Because if you're being slightly less specific, that it's only that, all right, or only Mr. Goodbar, all right, you are combining those two things, which realistically means it's this and this, it's crackle and dogs that you have to take into consideration. This little and symbol is what it's supposed to be. All right, so how many crackles and how many special dogs are there combined? Well, it would be basically 27 plus 19. That's sum. And in which case you would get 46. 46 out of 105. Again, if you went through the process of dividing them, 46 divided by 105, you'd get this as a decimal, 0.438 something. And if you then took the time to multiply by 100, the effect is to simply move the decimal place twice towards the right. And you would get 43.8 something %, which again you could round it. Right? So about 44%, which is under 50, right? Maybe you wouldn't bet money on that, all right, but not bad. Okay. Now the last one, we'll use that other formula. And I'll put that here. There's more than one way to do this problem, but I think the formula would be the most practical. C. What is the probability of not a milk chocolate? The number of the outcomes favorable to the event over the number of elements in the sample space. Okay. You could figure it out by combining the things that are not milk chocolate. If you wanted to, right? In which case it would be 105 over the sum of these things. What's not milk chocolate? The 27 crackles, the 26 Mr. Goodbars, and the 19 special dogs, right? Nothing wrong with doing that. But you do have a formula as an alternative to calculate. And there's this to generalize. All right, remember, the probability of not A, this is an alternative, is equal to 1 whole minus the probability of A. Right? It's just that A, in this case, is milk chocolate. Right? So the probability of not milk chocolate. Right? The probability of a milk chocolate is still this, n milk chocolates over n in the sample in the set, which in this case is just this number, 33. 33 out of 105, subtracted from 1. When you have a situation like this where you have a fraction that is being subtracted from a whole number 1, in theory, if you're doing this by hand especially, you would have to convert this to an equivalent fraction that uses the same denominator. So you would basically express the quantity of 1 whole using whatever the denominator number is. So if it's 105, think of this as being 105 sitting on top of 105. To divide the top by itself would be 1, right, as long as it's not 0. And then just subtract these numbers, right? 105 minus 33 produces this, 72 over 105. Remember, when you're doing subtraction, of fractions, you just, once you've matched the denominators, you just keep it. You don't combine them. Okay. Anyhow, the decimal number would be this, 0.6857, whatever it is. All right? And times 100% would move the decimal place over, which would make it 68.5 something %, which is about 69. Okay. If you feel a little sketchy about fractions, all right, you don't have to do it this way, but of course you are armed with a calculator, all right, and it would do that work for you, although the skill is still very important, all right. This should produce the same result, all right, and because I'm a little temperamental, I can't help but want to verify that. So I'm just curious. 27 plus 26, 13, 53, plus 19 is 12, carry the 1 is 72. It would be the same fraction of 72 over 105, right, that you would get as a result of adding everything that isn't milk chocolate versus subtracting what is milk chocolate from a whole, all right? You get the same fractions. Okay. All right. The last thing, and I'll cut it off now, is regarding experimental probability. I think that this table that you can print out very much explains it clearly. This is the table, right? This is explaining that there is a difference, right, in real life very often between what is the theoretical probability and what is experimental probability. And the result, and pardon me, the reason for that is because the person simply hasn't done enough of the experiment, right? If you did hundreds of the same experiment over and over again, the two numbers, the theoretical probability and the experimental probability, would get close together, right? Closer to together, and perhaps eventually the same thing. Mathematically negligibly different. All right, here, you see, here's a coin toss, all right? Again, there's only two choices, right? Heads or tails. Let's say that a person did the theoretical probability. If you were calculating whether you're going to get heads in this case, number of expected heads, out of 10 tries, right, there would be 5 heads, right, in the 10 tries, according to the calculation. If you did it 100 times, it would be exactly half. If you did it 1,000 times, it would be exactly half. If you did it 10,000 times, it'd be exactly half. It would be 50% according to the theoretical probability, no matter how many times you did this, all right? Then there's real life, which is the experimental probability. Here's what a person who did this experiment of flipping a coin a certain number of times got, all right? I got a head myself. I got a tail, 50-50, so far so good. I got a tails again. And I got a head, all right? Well, it doesn't always work out that nicely, right? Instead, what happens is this, all right? Actual number of heads observed. Observed is the key phrase here, because that's the experiment. 4 out of the same 10 tries, right? As opposed to 5 out of 10 tries, which is theoretical. That means in terms of a percentage that this only occurs 40% of the time when it should be 50. Then they did more experiments. And out of 100, 45, all right? It was observed 45 times that a person got heads, which in terms of a percentage would be 45%, not 50. All right, but notice as you do the experiment more and more, 1,000, 10,000, 100,000 times, not that anybody would want to do this on Saturday, right? All right, the numbers creep up, all right? In terms of a percent, it goes from 40% to 45% to, what is that? Almost 55%, it actually went over, right? And then on here, 49%. Right? and then it just get inching closer and closer to what it really theoretically should be, which is 50%. 0.497 is just shy of 50%. The bottom line is that you're going to expect, all right, you should expect a different result experimentally, even if it's slight, right, even if it's a lot, all right, than what is theoretically possible, all right, and that isn't anybody's fault, all right, it's just what happens. And what you need to do is the experiment more times, right, and you will see that eventually it'll creep towards what it is. Anyhow, I cut this out because I thought it was very helpful. There's this law here, the law of large numbers, right? All right, the law of large numbers states that the probability statements apply in practice to a large number of trials, is the key phrase there. All right, not to a single trial. It is the relative frequency over the long run that is accurately predictable, right? Not individual events or precise totals, all right? So these two things, theoretical and experimental probability, will eventually match in the long run, right? Not immediately, okay? So you might print that out for reference, okay? And that's it for today, okay? Let me leave it at that, all right? Good thinking of you, even if I can't see you. Take care, folks. I'll see you on Monday. All right, just try to work on section 11.1 at least. All right, we didn't really finish 11.2. I only sort of touched upon it. All right, but this week I'm going to try to record a cumulative average. So if you can, try to catch up to at least section 9.3. All right, try to do 11.1 if you can, if you really do have the time. All right, and the way that Canva's gradebook is rigged, it's not going to hurt you. All right. Whatever the highest recorded quiz grade, that's what my cumulative averages are, all right, will maintain that status, all right? This is just the opportunity to improve your grade if you need to, okay? And you want exposure to the material, naturally, okay? So I'll see you next week. Be safe.